Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today, it's our great pleasure to have Professor Michaela van der Scheer from UCLA to visit us and give us a talk on a brief synopsis of her recent research at the Multimedia Communication and System Labs at UCLA. We will first hear Michaela to give us a brief overview of her lab, and then hear detailed talk from two of her students, Yisu and Fangwen Fu. Professor Michaela van der Scheer has won numerous awards. During her career, she has won 2004 NSF Career Award, 2005 Best Paper Award in IEEE Transaction on CSVT, 2006 Okawa Foundation Award. She is IBM Faculty Award winner for year 2005, 2007, 2008, and won the 2008 Exploration Stream Analytic Innovation Award from IBM Watson in year 2008. In 2006, he won the Most Cited Paper Award from European EuroSIP Image Communication Journals. She was associate editor of a number of IEEE transactions, including IEEE transaction on multimedia, signal processing letters, circuit system for video technology, and signal processing magazines. She held 32 issued U.S. patent and 3 ISO award for her contribution to MPEG video compression and streaming. Her research interest spans through multimedia communications, networking, processing, and systems. Without further ado, let's hear what she has done exciting work in her lab.
Thank you, Jean, for the introduction. So what my plan is today is to give you first a brief synopsis of our recent research at UCLA in my lab. But my plan is to give you mainly a synopsis of what we are doing without getting in an awful lot of details in view of time. However, I'm going to have two students that are going to give more detailed talks after that. And actually what I hope with this presentation is to catalyze enough interest from you such that maybe when you come to UCLA, you are visiting us and you can find more details about our own research while visiting us, or maybe to invite us to give more detailed talks on any of the topics that you may find of interest here. Okay, so I'm going to try to start with a brief highlight of what is our research all about. So our focus in the last couple of years has mainly been to come up with a rigorous framework to analyze, design, and optimize, and I'm going to stress dynamic and heterogeneous multi-user environments and applications. So actually starting with 2004, when I moved from industry to academia, we started actually to look in our group and trying to find a new theory together with algorithms and designs. But the main focus was in trying to find a new theory for architecting next-generation wired and wireless networks, and as well as distributed systems which are interconnected through such networks, which are able to support media applications. So in this research, a main key theme is multi-user communication and networking. And what I'm going to do today is I'm going to go through a couple of the topics highlighted here in red. So I'm going to talk a little bit about some of our new designs for multi-user communication in wireless networks. I'm going to talk a little bit about how we can reduce power significantly in wireless multimedia systems. I'm going to briefly touch on our work on peer-to-peer networks, as well as some more recent work on distributed stream mining systems. There are also some other topics we have been working on, but I'm not going to talk about those today. However, one of my students, Fangwen Fu, will touch on the topic of wireless media communication. So if you look at really multi-user communication today, most of the protocols we have are really kind of passive, and they're really adhering to some predetermined rigid protocol rules. Also, alternatively, another type of design that has emerged in recent years was to really model transceivers as rational agents competing for resources, scarce wireless resources, for example. And that's what game theory tries to do. However, if you look at the current solutions in game theory today, they can be kind of classified into categories. On one hand, we have cooperative games that eventually, most of the time, either require a lot of message exchanges to ensure that the users are going to be able to operate on the Pareto boundary. In here, I'm actually having two users, just two users for illustration. And they have utility U1 and U2. And if they would like to operate on this Pareto boundary, most of the time, either a moderator may be needed, like, for example, an access point or a base station, or this could be also done in a distributed fashion, but through heavy message exchange. If you don't want to have this type of infrastructure or message exchange overheads, what we have is solutions which are based on non-cooperative approaches, which are doing a myopic best response. And what we know about this type of games is that for some of these games, we can prove that a Nash equilibrium exists. But this Nash equilibrium, which is based only on myopic based response on local information, is for most games very inefficient. So for most communication games of interest, the Nash equilibrium is not on the Pareto boundary, but rather very far away from it. And at times, it may even lie at 0-0 utility, as I'm going to show in an example a little bit later. So the first thing I'd like to point out is that most of the work is focused either on fully collaborative information exchange or kind of almost passive best response, myopic response based on local information. Also, the focus is really on equilibrium characterization rather than constructing new solutions that would allow us to operate maybe based on local information but close to the Pareto boundary. So what we would like to have is constructive design that would allow us to move this point towards the Pareto boundary but without any message exchange. So that should be possible mainly because in reality these devices that we talk about are increasingly smarter. We have smartphones and smart gateways and smart devices, which are heterogeneous. Increasingly, they are strategic. They may not want to just comply to existing protocol rules, but they may want, within the framework of a particular protocol, to maximize their own utility. They are capable, really, to proactively acquire information and also learn, build beliefs, and also select desired equilibria. So they may work together to achieve what I'm going to call here as co-opetition. So there may be non-cooperative users aiming to maximize their own utility, but which may discover in this process that it is better for them to move towards a cooperation. And I'm going to talk about it in just 1 second. So co-opetition stands for cooperative approaches by non-cooperative users, so non-cooperative users. But what we would like to do is we would like to see in which cases these users are going to be able to cooperate or coordinate to achieve better outcomes. And what we see actually in the literature is there is very little work in the communication area in trying to find out better equilibrium concepts and better solutions to achieve this better equilibria. So why we would like co-opetition is because the strategic devices really compete for the available resources, and that may often result in inefficient outcomes. For example, this inefficient Nash equilibria. However, if you have coordination and cooperation, then both the network efficiency may improve, but also in many cases, if the network is well designed, the performance of individual users, of all individual users, may also be increased. So what I'm going to call coordination is the design of protocols that better utilize available information to coordinate spectrum access or resource access, but without explicit message passing. So there will be no message exchanges involved. On the other hand, I'm going to call cooperation the design of protocols that shape the incentives of users, agents in this case. I'm going to call the wireless devices or the network devices as agents. So shape their incentives in such a way that their selfish behavior results in cooperative outcomes, that it becomes in the self-interest of users to come up with cooperative outcomes. So what we'd like to do is we'd like to have devices that are able to learn to determine when cooperation or coordination may be beneficial. And if that's the case, to coordinate among themselves to select desired equilibria, which are beneficial in terms of efficiency, fairness, as well as stability. So, for example, what we show here is a wireless device or a device that will interact with the environment that may be dynamically changing over time, and it's making observation based on this information. And based on that, it may make beliefs about its coupling with the other users, how its actions affect in the short term, but also in the long term, their performance. And based on that, they can determine the policy based on which they would like to interact in the future with the environment. So that is based not only on information about, let's say, traffic or private information of the user or private valuation of the user of a particular resource, but also on how this particular user is coupled with other users in the network and how he is affected and can affect other users. So coupling among users is key in this type of interaction. Also, we're going to do a lot on trying to determine not only just to characterize an equilibrium, but try to select equilibria. And that may depend on really the device's ability, heterogeneous ability maybe, to acquire information and learn, but also the achieved performance at a particular equilibrium, both from a system performance, but also from an individual user's performance. And finally, we'll be interested in convergent properties, both whether we can achieve local stability or global stability, and my student Isu will talk much more about that in a particular setting. So kind of to finalize this introduction, our goal is really to look at different transceivers having different private knowledge that are trying to dynamically coordinate maybe, cooperate maybe, or maybe compete to gather resources such that they maximize their utilities. And what we have seen in our recent work in the last couple of years, that this really can achieve unprecedented improvements as opposed to current existing solutions of protocol design, which rely on rigid predetermined rules for interaction. So let me start by giving a brief overview of some work that we did in this area of multi-user communication and networking. And I'm having here a couple of the students that have worked in this area, inclusively Isu, who will give a presentation later. And the type of problems of interest in this area are really new theory and protocol design to achieve this type of cooperation and coordination in multi-user access networks. And really the vision is to better understand the coupling existing among the decision-making made by the users in this type of networks, and design the next generation MAC protocols that can help us improve, again, not only network efficiency, but also fairness and stability. And last but not least, which may be strategy proof, meaning that there is really in the self-interest of the users to comply with the protocols designed, rather than manipulate them. So I'm going to start with exactly this last topic. So I'm going to talk first about just give you an example about how we went about to solve selfish behaviors in wireless networks. So we know that network protocols can be easily manipulated by selfish users, which may not necessarily want to destroy the network, but they may just want to maximize their utility. So they are self-interested. And this leads to a result very often that's called a tragedy of commons that has been studied by many people, inclusively in the CSMA-CA scenario by Kajal and others. We have looked actually at a similar scenario in the TDMA case, but I'm going to focus today just in view of time on the CSMA scenario, just because it's faster. So really, what we would like to do with this work is to come up with solutions that would help us avoid these inefficient outcomes. And we would like to have a network design method that would help these selfish users to choose cooperative outcomes. So for that, you would say, well, you're going to say, well, but we have solutions for that. Pricing schemes have been designed to do just that. So a widely discussed method to incentivize users to really come up with cooperative outcomes in competitive scenario is really pricing. And that has been studied for a long time in microeconomics for decades. And it is known that if you do that, the outcome can achieve the system optimum. And the way it works is by having prices that capture the external effects of a user's behavior on others' welfare. Hence, when facing these suitable chosen, and I want to emphasize suitable chosen prices, is equivalent really to taking the effect of one's behavior onto others into account. So for example, what we have here is a user I, may try to maximize its actions over its action set. So for example, its transmission probabilities in a wireless network. To maximize PI, which will be the new utility, which will be the utility of the user. So for example, the performance or the throughput that he's going to gain, minus a cost, minus a price he needs to pay for using these particular resources. So by introducing this taxation, we are hoping to try to really account for the inconvenience caused to others. However, how we can interpret these prices in a networking scenario? For a long time, while looking at prices and taxation, I was not very comfortable with it. I didn't feel it was a good solution, really, for wireless networks. And the main reason I started to ask this is because, really, how we can interpret these prices and payments in wireless scenarios. So, for example, one way to interpret that would be to view these prices as a coordination signal, like done in the work by Kelly, for example, or Lowe. In this case, the signals are really for coordination in decentralized methods to find a global solution to this optimization problem. And however, for a pricing scheme to be effective, these users need to follow the prescribed scheme. They are still going to be needing to align themselves with this prescribed rule. So hence, this becomes inconsistent with selfish behavior. Also, it has another disadvantage. It requires users to exchange messages to determine the desired price, which for wireless network would be disadvantageous. Another interpretation of these prices in networks was as real payments of some good. And that's, for example, the work of Varian or the other work of Kelly, where really they tried to view these payments as really some form of monetary payment that's exchanged among users. However, the question becomes in a networking scenario, what good do users really care about? Should it really be money? And really, why do users agree to pay prices? Because in order to be able to have enforceable payments, we really would need to have some form of contracts. If we don't have that, then users may free ride, and having contracts may require a lot of infrastructure addition to current networks, which we may not want to add. So another problem is that really, if these users do care indeed about these goods, because we assume they should care, otherwise they will have an incentive to free ride. If they care about that, then these payments or rewards will reduce or will increase the welfare of the users or of the network provider. So really, it becomes a difficult problem to compute the right price for these different types of users and to come up with the right infrastructure to implement taxation and pricing. And especially if private information of users is involved, private valuation of resources of goods, this becomes an even more difficult problem. Last but not least, in many situations, it has been shown, for example, by Johari and Tsitsiklis, that price-taking behavior is not really consistent with selfish and strategic behavior. Most of the users will not be price-taking, but rather price-anticipating. They can understand how their actions will affect future prices. And based on that, they are going to derail, really, this type of process of implementing prices to achieve network utility maximization. So what we searched for a long time was really an alternative to prices. So we would like to have pricing schemes which are not necessarily suffering from these disadvantages mentioned before. So what we propose is an alternative to pricing to sustain cooperation among selfish users, for example, in the case of wireless networks. And what I'm going to give to you today is just a simple example of where we implemented this type of scenario for a slotted Aloha protocol. However, this solution that I'm going to describe next can be implemented in other scenarios that go way beyond just Aloha. So again, just for illustration, I'm going to consider a very simple slotted Aloha scenario where I'm going to model the different wireless users transmitting their data as a non-cooperative game with having a number of users, a strategy of users, which is actually going to be the probability of transmitting, the payoff of the users, which is going to be internal valuation of resources, KI, let's say, of how much they would like to receive a particular amount of traffic, transmit a particular type of traffic, times the probability of transmitting, times the probability of the other users not transmitting. So if you like, this is the good put of a particular user multiplied by a valuation KI. Yes, please.
Your use of the word transmission, can we replace reception in this model? Like the YouTube nightmare scenario where everybody wants to, I want my video and I don't care about him.
Exactly. Yes.
Thank you.
So it could work in a transmitter-driven scenario, but also it could be viewed from a receiver's point of view. Yeah. And as I'm going to show just briefly a little bit later, it can be even from a relay scenario. So it could be a gateway somewhere in the network as well. So there could be different levels of hierarchies of both competition as well as coordination among different entities, transmitter, receiver, gateways. OK, but I chose this scenario just because it's awfully simple to explain the key idea. So in such a scenario, let's assume we have two users, but the result will hold for many users as well. So I have user 1 and user 2. And what is well known in such a scenario is that the Nash equilibria of such a slotted aloha games are these orange lines in here. And as a matter of fact, the most likely outcome is the 0-0 outcome. So nobody will transmit. This result is known. Collision will always occur. And actually, the users will get no traffic transmitted. So what we want is to find this method to support efficient outcomes without message exchanges or message pausing. And we would like to do that without pricing. So one way to do that would be through the implementation of an intervention function. So what this is the current, yeah?
So that blue region is?
Oh, I should explain a little bit better. So this blue region in here would be all the possible outcomes all the way to the Pareto boundary, which would be possible if users would be able to coordinate. Okay? So they would be willing to time share the network.
So why isn't it convex?
So in this particular case, we are going to use this type of utility function. Yeah? So there will be no, unlike the TDMA case, where I'm going to have something like this, yeah, where the user will time share the network. In this particular case, I'm not going to have coordination between users through explicit, let's say, outside entity, but rather I'm going to have users in a distributed, decentralized manner accessing the network.
So because you can't time share?
Yeah, I cannot time share. Ideally, I would, and I'm going to talk a little bit about that later, I'd like to have a way to coordinate among each other such that I can operate like in the TDMA scenario, and I could time share. However, here everything is done in a, let's say, this would be like the current H0211A scenario, kind of a DCF scenario. It's a little bit simplified here. I'm considering a slotted aloha. I don't have sensing, but it would be quite similar to that. So what I have is I have users not sharing any information, just determinate transmission probabilities. So this is the current contention games, like used in current wireless networks, like H0211 networks. And what we would like to do is we would like to introduce a new type of game, an intervention game. I'm going to call it for now Stackelberg contention game, where the following will happen. I'm going to augment this type of game with a manager, or better said, a policer. And this policer, what he's going to do as a first step is he will announce an intervention function. Or this intervention function could be known a priori. So he will say, I would like you to behave according to this rule G. I'm going to go into more details about how this intervention rule can be defined in just 1 second. But let's assume that I'd like the users to, for example, behave cooperatively, such that they can operate on the Pareto boundary. And I'm announcing this rule. And then the different users, knowing this particular rule G, they will determine their transmission probabilities. However, if they do not comply with my rule G, then only this policer will intervene and transmit. So what I'm going to introduce is a method to really tell users what is desired from them. And in the case they do not perform according to my desired rule, I'm going to punish them. Let us go and understand this a little bit better. So I'm going to give an example. For example, for this particular game, I chose a total relative deviation. So what I'd like to have is I'd like to have an intervention function where the total relative deviation of all the users needs to be minimized, for example. And what I'm going to show is in here the utility of a particular user, user I. And ideally, what he would like to do to maximize his utility, if I don't have an intervention function, would be to always transmit. So the best for a user is always to transmit, as we have shown in the previous slide. However, what I'd like a user to do is to transmit only a certain amount, such that I have the users actually time-share this network, and hence there is nobody cannibalizing the network and transmitting all the time. So the way to do that is by implementing an intervention function which would shape this utility function of the user rather than being increasing. So conventionally, if I don't have any intervention, the user's utility will just increase as its probability of transmission will increase. However, if I'd like the user to operate only at this particular point such that he's time sharing the network, then what will happen is I'm going to have the payoff being shaped actually by this intervention function. So this red curve in here will indicate the new shaped intervention function through the use of this intervention user. So it will reshape the utility function of the users such that it becomes in their own self-interest when they try to maximize their utility to operate at the desired operation point. What is interesting to see is that, and that's I think important, the level of intervention is 0 at equilibrium. It really will be not an intervention. The intervening user will not intervene. He will only do that when the user misbehaves, when he starts to transmit above its prescribed transmission probability. So at equilibrium, it is in the self-interest of the user to maximize its utility to operate at this prescribed level, and hence this intervention will not be taking place, but it will only serve as a threat. So if you look at, again, at the differences between this type of work with conventional work done by a set of other people, that's really quite different than conventional Stackelberg games. And actually, after we named it Stackelberg game, we kind of almost regretted of calling it Stackelberg because it may be confusing. So in conventional Stackelberg games, what people do is the following. They have a leader, and this leader will have a fixed action. And given this fixed action, for example, the users will go to respond. And the manager is really the leader, and he will use resources. So if you look at the current existing games using Stackelberg strategies, the manager will use resources to implement the Stackelberg strategy. However, in our case, what will happen is quite different. First, what the leader will do, so what the manager will do, it will be a contingent plan depending on the follower's choices. He may decide to intervene, and how much to intervene will depend on how much these users are going to access, depending on the probability of access of the network. Also, the manager may not intervene in equilibrium. Only a threat will exist, so resources are not used. There is not overheads involved to putting this manager. Also, I want to say that here, for simplicity, I assume there is a manager, but this could be also implemented in a distributed way. You don't need to have a manager. So alternatively, this convention game, as opposed to conventional games, can be viewed as a Stackelberg game with multiple leaders. So conventionally, we have one leader and multiple followers. Here we have the reverse. We have multiple leaders and a single follower, the manager. And the manager will decide how eventually he will punish the users depending on what the leaders, which are the users, have done. So this is actually giving users incentives to behave appropriately. And this type of method could be used really beyond just the simple scenarios I described here. We have looked at ad hoc networks, multi-hop networks, and in more recent times, for example, even as mitigation of attacks by malicious users. And it can serve the purpose of coordination as well as providing incentives for cooperation. But that was not shown here. However, I'm going to talk briefly about coordination now. So let's assume that we don't want necessarily are not concerned with users manipulating their transmission probabilities. So what we rather have, we would like to have them coordinate, such that we address the question that Phil just asked before. What happens if we would like them to operate, like in the TDMA scenario, would like them to time-share the network, but without having a controller and without having message exchanges? So how can user in a distributed manner coordinate to access the spectrum and efficiently share the spectrum? So there will be a trade-off between the degree of coordination and the amount of communication overhead. If you look at the current solutions, we have on one hand TDMA, where coordination is achieved by a central scheduler. So we have both message exchanges, but also we have an infrastructure. On the other hand, if you look at slotted Aloha CSMA protocols, then everything is distributed, everything is decentralized. There is much less coordination, so it means that users will very often collide. So the performance will be less than in this case. So what we would like ideally to have is protocols that are distributed and decentralized like this, but which achieve such type of coordination. So we were able to do that, and the way to do that was through utilizing protocols with memory. So in the course of interaction, users receive different types of feedback. I'm going to give here just one example. They may know whether the channel was idle, whether they sent a packet and it was successful, or if it was a collision. Of course, you could have more refined feedbacks, and they could be taken into consideration to further improve the network. But for now, we are going to assume just such a ternary feedback. The probability of a user transmitting is determined then by both its recent transmission decisions as well as the feedback information. And when designing these protocols, we looked at two things. On one hand, we would like to maximize the throughput. We would like to be as good as TDMA in terms of throughput. But also, we would like to have a low delay. And we define as delay the average number of slots that the user needs to wait until its first successful transmission, okay, from a randomly chosen slot. So coordination can be achieved using memory in our method by correlating successful users in consecutive slots. So what we're going to do is something very different than the current H0211 DCF scenario, for example, or what current Macs do. We are going to have a successful user transmit with a high probability, while if he's successful, so a successful user, which was already successfully transmitting data, will transmit with a higher probability, while other users, which are not currently transmitting, will transmit with a low probability. And of course, as we allow a longer capture of the channel by one particular successful user, the total throughput will increase, while delay will also increase. So hence, we will have a trade-off between, on one hand, efficiency, and the other hand, delay, or if you like, equity among the users, because they will not be able to access the channel as fast. Also, as I'm going to show briefly in the next slide, with proper design, a fully distributed MAC protocol, which would have an n-1 period, where n is the number of users, can achieve outcomes in a decentralized way, which will be as good as a centralized Aloha. So let us consider protocols with memory 1 just for simplicity. So what I show here is, on one hand, the total throughput. So this is percentage, so it's the total channel utilization. And this is expected average delay. And here would be TDMA. TDMA would fully utilize the channel, and it will have minimum delay for the users. However, again, as we said before, it will involve some form of message exchanges as well as an infrastructure. On the other hand, what we have here in red is the protocols currently in use without memory. And for example, what we have here is an H0211 DCF protocol being drawn. In green, what I'm showing is a state-of-the-art solution which would use some heuristic methods to exploit some form of memory by Columbia University. And what I'm showing here in blue is a first algorithm which will use just a memory of 1. And what you can see is actually we'll have a trade-off between having, on one hand, a low delay but a limited throughput versus having almost as good a throughput as TDMA, but with a higher delay. Here I'm going to show only the protocol with memory 1, but we have nowadays protocols that would be able to bring this towards the TDMA scenario. Now, why is this shape like this? Well, the reason is that, oh, by the way, this is for 5 users, and again, these ternary signals feedbacks. So for this particular scenario, the reason the curve is going down is because a success lasts for only 1 slot. Hence, if there are many idle or collision slots between successful transmissions, then what we are going to have as total throughput is that as the total throughput increases, the idle and collision slots reduce, and as a result, the delay will decrease. So that's the reason why the delay decreases in here. However, on the other hand, on this other side, I'm going to have more successes and less collisions. However, a success of a user lasts for several slots. So hence, there are a small number of idle or collision slots between two streaks of success. This will lead to a higher throughput, but also to more delay. So you can see there is this trade-off now between, on one hand, increasing the throughput, but also increasing beyond the point the delay.
I assume E will give a more higher resolution, detailed explanation of the protocol.
No, this is work done by another student, Joe Park.
Okay, so maybe
we can refer you to details of all of this in some of our publications.
Okay.
Love to.
So maybe you can basically just briefly explain what are the collaboration protocols. So you basically remember in the last slot whether you collide, whether the channel is empty or something, right?
Yeah. So my memory is the following. I'll know whether the spectrum is idle, whether nobody is transmitting. I will know whether I had successful transmission at the previous time slot, and I will know whether I had a collision.
Okay.
Kind of very similar with the current protocols we have today, like CSMA.
I thought you should have a false signal, which is basically the channel is occupied by someone else, right?
I could use, so what I have right now is I have idle or not. So I know whether the channel is occupied or not.
Okay.
Yeah, so I know it's occupied or not.
Okay.
And if I transmit, I know whether I was successfully transmitting or not.
Oh, collision. Okay.
Yeah.
So,
So I know in the idle case, is it used or not?
Okay. And what are the decisions?
Okay. So the decisions are as follows. If a user successfully transmits in the previous time slot, then it will have a higher probability to transmit again.
Okay.
So capture the channel. On the other hand, if users are going to transmit, not transmit at the current moment in time, they will transmit with a low probability.
So,
and note that this is quite different. This is quite different than current protocols, which, sorry.
Okay.
Again, view of time, not going through all the details, but we would love to show you more of the details. Okay, so if you look at this set of protocols with memory, would have the advantages of both worlds. On one hand, we are going to have performances if we increase the memory. I just showed you memory 1. But if you increase the memory, we are going to achieve as good performance as TDMA without message passing. So the message overhead will still keep small. On the other hand, if you are concerned about the amount of memory, then you may have maybe performance which is only in this region, as I showed in here. With memory 1, you will need to make a trade-off between, on one hand, having throughput, which may be as good as TDMA, versus delay. However, if you increase the memory, this curve goes towards TDMA. So we introduced these memory-based transmissions in MAC protocols, and they require much less overhead. Actually, it requires no overhead compared to the TDMA type scheduling. And by varying the level of memory, we can obtain a variety of performances in both delay as well as throughput. And these protocols with memory can be applied to various scenarios besides the example that I just gave now. For example, we use them for event-driven networking as well. Now, to go back to a question that I got before from the audience, some of these methods could be implemented not only at the transmitter side or receiver side, but even within a network. So for example, I have another student of mine who looked at how we can have distributed spectrum management in relay networks. So we may have a base station in here, but we may have multiple users transmitting through each other to a particular base station. And then our goal in this project, which is a kind of new project for us, was to have users autonomously determining their power. And what we would like to do is we would like them to specially reuse the spectrum. So we would allow simultaneous transmission of users. Also, we are going to use amplify and forward, which is low cost, unlike, for example, decode and forward methods used by other people. We would let the nodes smartly interact with each other, meaning that they would like to optimize the spectrum in response to interference. So hence, what we do in order to optimize such a setting is, again, we rely on these non-cooperative approaches. We model this as a game where the relays are the players. They try to determine their power allocation on the various channels in order to maximize the achievable rates. So every user, I, will try to determine this power, which will maximize the achievable rate given the interference of the other user, given the power that is allocated by the other users. So what we have proved in this type of scenario is that in such settings, at least one equilibrium exists, and determine the conditions for convergence for such settings, and design low-cost protocols that are able to converge. And while doing that, the performance of these protocols was shown to be better than conventional approaches such as equal power or TDMA. And also, if we compare to other existing solutions for spectrum management in networks, for example, work that does special reuse of the relay slot, or auction-based power control, or, for example, simple two-user settings where people have used much more complex schemes such as decode and forward, what we can see that in terms of spectrum efficiency, signaling overheads, and cost, our methods has the best performance versus cost trade-offs. So we achieve a high spectral efficiency at a low signaling cost. Actually, we don't have any signaling cost. It's a fully decentralized framework. And it's a very low cost because we relied on just amplify and forward techniques. Now let me move at a different topic. I talked quite a lot about multi-user communication, but what I want to do is now talk briefly about power-constrained transmission in wireless media networks. And the work here is done by a set of different students, and the main goal here was to drastically reduce power in media systems. And the goal was to be both application aware, as well as try to come up with designs which will reduce both the transmit as well as the processing power. And the solution was really to deal with the dynamics introduced by both the application as well as by the dynamics in maybe the power consumption or the wireless channel, to learn these dynamics online and come up with a runtime stochastic optimization that will try to maximize the quality of the video data, for example, subject to whatever power constraint we may have. And really the overall goal here was to come with a shift in the current design for media systems where layers now are able to interact with each other. It's a different type of interaction as in the previous slides. In the past, users were competing with each other. In here, we have different layers of the protocol stack. So if you like, the different agents are cooperative. They really try to cooperate with each other. So they would like to take into consideration their dynamics at different layers. And based on that information, they would like to reason and interact. So the idea would be to have, based on this interaction and learning, methods that would lead to smarter design at different layers of the system stack. So just to give an example, here the layers are no longer application layer, for example, MAC layer and physical layer, but rather the layers we talk about is the application layer, OS layer, and the hardware layer. And our focus is, again, on trying to maximize, for example, the media quality under traffic dynamics, given whatever power constraints we may have. And the type of problems that we have looked at were both ray distortion, power control, as well as power management, like, for example, dynamic voltage scaling, as well as work such as resource allocation and scheduling in the case we have multiple tasks. We have also looked at the case where this hardware is faulty. So we may have errors in the hardware. And in that case, what we would like to do is still be able to utilize these ICs rather than throwing them away, try to compensate for them at the higher layers. And if you look at the common solutions used to deal with this system problem, the key idea for us was no longer just act based on current information, but rather consider how the current dynamics will impact future dynamics as well as future decisions. How, for example, the decision of switching to a different power level or switching off my transmission, my RF at this moment in time will impact not only current performance but also future performance as well as future costs. So this is what we call foresighted decision making. To deal with these dynamics online, we rely on reinforcement learning solutions. And this is kind of different than conventional. When people talk about learning in the past, they mainly talk about model-based learning or learning based on, for example, maximum likelihood estimation or even our own work on adaptive linear prediction. So most of the time what we have is we have a layer, for example, the application layer of the OS layer, looking at a particular type of dynamics, for example, traffic dynamics or CPU dynamics, estimate the current conditions, and based on that determine a local policy, local to this layer, and decide what is the best strategy to act upon at this particular layer. Rather, what we would like to have is the proposed solution would rely actually on repeated interactions among these agents and the unknown dynamics at the different layers of the protocol stack. Also, what we are going to do is we are going to rely on model-free learning techniques, on reinforcement learning techniques. So we are going to have interactive learning. We are going to try, without having a model, to learn these different dynamics online. And based on that, also these different layers are going to be able to interact with each other and exchange messages. So our focus in this work is what is the minimum amount of message exchange I need to have among layers to enable to maximize the utility across the different layers of the protocol stack. And the reason this is challenging is because these different layers of the protocol stack operate at different scales. So for example, the application layer may operate at a very different scale than, for example, the OS. So hence, what we would like to do is deal with this type of asynchronous behavior and have a distributed control which would be able to achieve the maximum performance. And Fang Wen will briefly talk about some of this work, but not in the context of this problem, but rather in the context of media transmission. Let us look how good these methods really are. So what I compared here against is, I'm going to compare mainly against work done by Professor Clara Narstedt and others at UIUC, where they adapt all the different layers of the protocol stack, but they are doing that myopically. They just look at what happens and react based on that. So if you look at what happens for the particular scenario considered here, is the performance of the video transmitted is only 31 dB. So it's really quite low. However, on the other hand, if you look at the performance we can achieve by applying these foresighted decisions, the performance is significantly improved. And the reason is as follows. What we are doing is, actually, we are able to capitalize on the fact that current actions we are making will impact future decisions. And these future decisions will have implications at also other layers of the protocol stack. So this is becoming very important. So it's not only about cross-layer optimization, but also making decisions, understanding how these decisions we make at different layers impact the decisions at the same layer over time, but also decisions at other layers over time. Finally, let me move at another topic, peer-to-peer networks. We did quite some work in recent times with a student that just graduated on this topic. And the main idea there was not necessarily looking at media, but rather trying to come up with just better resource reciprocation strategies, how users could determine their upload and download rates in dynamically changing environments. So if you like, coming up with a better BitTorrent type algorithm. So what we wanted to do is we have optimal solutions for resource reciprocation among peers that are interested in the same content. And we would like to have a method that's both rigorous and analytical. So not only simulation-based, but rather we would like to predict the outcomes that we can get. And that would be able to deal with dynamic interactions, so peers coming and going, as well as with heterogeneous peers, so peers having different uploads and download rates, that are self-interested, that try to maximize their own utilities, and they act autonomously. So there is it's a distributed scenario. And the solution there was to really model this type of reciprocation as a stochastic game, where peers, again, are going to play their game. The actions that are going to be involved by the users playing the game is how much resources they will reciprocate and to which users they will reciprocate. Also, which users they should choke or should unchoke. And they will determine that in the framework of the stochastic game by making foresighted decisions. So they will not only look at the current impact on the performance, but also how their performance, how their selection of actions, which peers to choke, to unchoke, to whom they should transmit information, more information or less information, will have an impact, not only short term, but also long term. So the goal is, again, to maximize the utility among these repeatedly interacting peers. And for that, of course, in order to do this long-term optimization, you really would like to have an efficient method, a robust method to model the peers' behavior. And we do that, again, using online learning. The good news about this is that in more recent times, we have the computer science department being interested in implementing some of these frameworks. So they have implemented this in actually Planet Lab for us. And the current results we have are very promising, significant improvements as opposed to methods such as BitTorrent or BitTyrant and other methods existing there. Okay, so this is really the last topic I'm going to talk about. This is, again, a more recent topic. The idea here is really trying to come up with some form of cyber discovery, if you like, in the case of distributed network processing units. So you can think actually about having multiple gateways, for example, everybody in the home having a gateway that will contain a particular amount of video data. And what you'd like to determine is you're interested, for example, in skating. So what you'd like to do is you'd like to go through a set of queries, whether it's a team sport, whether it's a winter sport, and all these different types of queries are linked together. And what we have shown is actually that these complex classifiers can be decomposed into cascaded topologies of such simple binary classifiers. But even more interestingly, if these type of classifiers are located at a particular processing node. So for example, a particular entity is specialized in solving this type of, answering this type of queries, while another entity is specialized in answering a different type of query. And these nodes are not collocated. They may be at different locations in the network. Then what we will have is we'll have processing operator that can be instantiated on distributed remote devices. And these devices may have their own constraints, resource constraints of answering a particular query or processing this a large amount of queries in a certain amount of time. So what you can think about is not only one query being solved at a particular moment in time, but maybe multiple queries simultaneously being solved. So hence, these processing nodes may be congested. The problem then becomes, can we, for example, maximize the joint classification quality across a large number of queries, subject to maybe resource constraints by the processing nodes, delay constraints? I may want to answer a particular query within a certain amount of time, maybe a couple of seconds or a minute. The dynamics of the traffic coming through the different classifiers. And also, since these classifiers may be at times located at different locations, how am I going to deal with these distributed decisions? Because at a particular node, I have a lot of decisions to make. I can decide, for example, to operate at a higher accuracy, to come up with a better classification of the data, but this may involve a longer amount of time for processing. So there's a trade-off between the accuracy of processing data versus the time associated with processing the data. Moreover, for certain types of queries, even the order of these types of questions, of this type of classification decisions could be changed. So what we have is a joint decision on one hand of a topology, so if you like, is a routing problem, but which is combined at this stage not only with routing, so a certain topological mapping of these different classifiers, but also the processing involved at every classifier. So as opposed to conventional, let's say, routing problems, the problem is here not only routing the data, but also how I should instantiate, what should be the operating point at every classifier, because each one of those will lead to a particular processing delay and hence buffering delay across the chain. So we come up here with new solutions for stream mining on both distributed routing, processing algorithms, as well as optimization and online learning. And some of this work has been done in collaboration with IBM Research Watson. Now, there are other topics that I didn't discuss here. Like, for example, we did quite a lot of work together with Intel on multi-hop wireless networks, mesh networks, mainly for campuses and larger homes. We did some work on cognitive radio networks by Fang Wen here, but he will not talk about it. We looked also at wireless media communication. Fang Wen will talk about this in his talk. Also, we looked at new cross-layer designs, new methods to do cross-layer design, as well as in more recent times at some new solutions for doing reconfigurable coding. I think Gary Sullivan talked a little bit about this in his talk, kind of a new paradigm for video compression. So to finalize, really, Many people are asking, well, how can we come up with a new clean slate design for the internet, for example, or for networking, and how we really can catalyze a new generation of algorithm systems and design. And it is our view that what we would like to do is we don't want necessarily to come up with, to throw away protocols and throw away designs, but rather just re-engineer these existing protocols and make them operate as markets where devices based on this private knowledge that they have can dynamically coordinate, cooperate, and compete. So don't have them as dumb devices, but rather as smart devices which can cooperate and compete. And maybe even design the objective functions of these users such that they are aligned to whatever objective maybe a network provider may have. So based on our results, we show that this really improves significantly the performance of the network. And again, E will go into a little bit more detail of how this is possible. So our hope is really that these devices now will no longer be passive transmitters or receivers or relays, but rather they will evolve and become smarter because they need to compete against other users or coordinate with other users, and there is an online learning process taking place. So the hope is that this will lead to theory as well as practical designs and add some new dimension to both communication theory, network theory, and also increasingly we believe that in game theory as well, because there the focus has been much less on equilibrium selection and much more on equilibrium characterization. Also, the work there has not considered constraints in terms of memory, in terms of message exchanges, which are very important for communication problems. Finally, I know I skipped for a lot of the material, even though I talked way too long. And if you're interested, I'd like to ask you to please go to our website, and from there you can find a link to our publications. And if you have any questions or any comments about any of our work, we'd be delighted to answer more of your questions.
You really have too much materials.
Too long.
I'm afraid to ask you questions because I think they will stretch the talk way too long. I actually would like to learn more about the Wi-Fi protocol, especially in particular. But I mean, I realize your talk is already too long for me to interrupt.
Maybe we can have the discussion after the lunch.
Although I think the time for your visit is too tight.
So I guess you either should come and visit us, or you should invite us. If you are interested in
I'll find the opportunity.
If there is a particular topic, so my purpose was to tell you different topics, but if you're interested in a particular topic, either I or I together with a student, we could come here back and give you more details. Also, he will talk now about some other types of protocols, other than the one shown here, but which are also able to improve the performance in wireless networks. So that may be interesting, and it will go in much more detail. Thank you.
Good morning, everyone. My name is Yisu, and I'm third-year graduate from the Electrical Engineering Department from UCLA, and I'm working in the Professor Vanasha's group. It is my great pleasure today to present my research work at Microsoft Research. So the topic of today's presentation is new perspectives on multi-user communications, which summarize our most recent progress in the understanding of how heterogeneous communication devices' information availability, decision-making, and learning capabilities have an impact of the performance of communication systems. So we start from a very high-level abstract of the current existing literature in multi-user communication theory. As Professor Vanasha just mentioned before, there are two main categories of this existing approach. First is called cooperative. Sometimes we have centralized manager and collect this information for all the communication devices and perform some centralized optimization to maximize some certain system-wide objective function. And sometimes we can also have some non-cooperative approach, and the outcome of such multi-user interaction usually corresponds to the Nash equilibrium. And it's well known that the Nash equilibrium might not be efficient. So here is the information availability issue. So the existing research always focuses on two extremes of the information availability, either local information or the global information. So however, in reality, we know that these communication devices might be built based on different standards or algorithms. And based on their hardware constraint, the ability to make the ability to make decision can also be different for different devices. So our question is that what if this happens, and how will the system performance of the communication system will be like. So in this talk, we'll use two illustrative examples, including multi-user wideband power control and also wireless random access. So here's the structure of today's talk. So we will discuss two kinds of communication devices. We classify the communication devices into myopic users and foresighted users, and we will address the definition of this myopia and foresightedness later. And we also have different assumptions about the information that this foresighted user possess, and we'll see how when the information changes, how the system performance will vary. So the first example we'll address is the multi-user power control scenario. So basically, we investigate this problem in the frequency selective interference channel setting, and it is it's a common setting in both wired DSL system and wireless OFDM system. So in this problem, the individual communication devices want to optimize their transmit power spectrum density function in order to increase their achievable rate in such system. And we are going to use the game theoretic design to study the performance. So here's the system diagram, and XIF represents, so basically it's a frequency selecting interference channel. So XIF represents the transmitted signal from transmitter I at frequency F. So HIJF represents the cross-channel gain from transmitter I to receiver J. So it's frequency selective, meaning that this HIJF is not a constant. It's a function in the superscript F. So it will vary from frequency to frequency. So its received YIF represents the received signal at the receiver J. Basically, it's composed of its desired signal from its own transmitter plus the interference signal from the other transmitter, and also plus the sigma IF here. Sigma IF here represents the noise spectrum density at the receiver side. So if we look at the user case received spectrum, basically it consists of several parts. The first part is the noise spectrum density at its own receiver, so it's indicated by the red curve. And the second part is the interference the other transmitter caused to him. It's basically the white space between the blue curve and the red curve. And also, it will receive its desired signal from its own transmitter. So for each individual user, he needs to determine how much power he needs to allocate in different frequencies. So basically, he needs to determine this PKF here. This represents the user case allocated power in frequency F. So each user is subject to a total power constraint. So the summation from all the allocated power in different frequency bands need to be less than or equal to this total power budget.
Just try to clarify. When you talk about this PKF, are you assuming the message is delivered to one target user, or he can send multiple messages to multiple users at the same time? We're allocating this message. Let's say I have, 10 messages in my queue, which is targeting to different users. Are you assuming in the allocation you're talking to multiple of them, or you're basically just assuming you're talking to one target user?
Oh, he just needs to talk to its own receiver.
Okay,
so,
okay. So basically that's one receiver. So basically here, you always has one sender and one receiver.
Right,
okay.
But they are simultaneously transmitting, so they are creating interference to each other. So the utility we define here is actually, we assume that each user will simply treat the interference from the other user as noise. So the total achievable rates, it can successfully decode is actually given by this formula. Okay. So here we have the basic infrastructure of the multi-user interaction. Then we can define it as a game. So basically we have number of players, and the action set is given by this one, meaning that each user needs to choose some transmit power spectrum density function that satisfies the total power constraint. And also each user's payoff is given by the achievable rate. So now we briefly review the existing research, existing solutions on this wideband power control scenario. And the first kind of approach is called a non-cooperative approach. And the most famous out algorithm is called the iterative water filling algorithm, proposed by people from Stanford. So from a single user perspective, given the noise and the interference power spectrum density, the best thing he can do is just to perform the water filling. So iterative water filling is just a multi-user version of the single user water filling. So the basic procedure for the iterative water filling is the following. So every user just randomly pick up some feasible power allocation, and usually this power allocation might not be the best response with respect to the interference that the other user caused to him. So at each iteration, each user will update his power allocation as the water filling solution with respect to the interference as the other user caused to him. And once he updates his power allocation, he will create a new pattern of interference to the other user. So he will perform this iteration over time. And people have shown that under wide channel condition, this iterative procedure will converge to a unique Nash equilibrium. So this is the so-called iterative water filling solution. In this scenario, each transmitter needs only to get the feedback from its own receiver of the interference pattern the other users caused to him. So there's no information exchange between different transceiver pairs. Okay, the other type of approach is called the cooperative approach. And in this case, they need to have a system manager which need to collect all these cross-channel coefficients from different transceiver pairs. And this centralized controller then will perform some weighted sound rate maximization problem. Please note that this problem is actually a non-concave problem, and which is very hard to solve, but people use some dual approach to handle this problem. So this figure shows the performance comparison between the non-cooperative approach and the cooperative approach. We can see here, for the cooperative approach, they need to have a lot of information exchange, but the performance is much better than the best-known solution of this non-cooperative scenario nowadays. So our question is that if we only focus on the non-cooperative setting, so users only have their local information about the interference pattern the other user create to him, can we do better than the iterative water filling? So now we will assume that some user gets smarter. He has the information about the water filling game and how he should to perform in such a non-cooperative setting. So this is the basic question. So we want to get some intuition from very simple two-user two-action game here. So we have a role player and a column player. For the role player, he can choose to play either up or down. And for the column player, he can choose to play left or right. So each element in each box, the first element in each box represents a payoff for the role player. And the second element represents a payoff for the column player. As we can see here, 2 is larger than 1, 4 is larger than 3. So if the role player wants to play the Nash strategy, then definitely he will choose to play down. So however, if he chooses to play down, and for this column player, because 1 is larger than 0, then he will choose to play left. So they will end up in a down-left play, which creates a joint payoff of 2-1 to both users. However, as we can see here, this up-right play actually will result in a strictly better payoff for both users if this role player to choose play up. So from this simple game, we can see here, this down-left play is actually the Nash equilibrium. However, if this role player, he gets smarter, he chooses to play up, then both users end up a better play. So which means that if user is myopic, he just take the action of the other user as given. He will play the Nash strategy. Probably this outcome will be not efficient. However, if this user gets smarter, he becomes foresighted, and he knows the actual structure of the game they are playing. He might choose another action which might benefit himself. So this is the basic intuition that we get from this simple game. Okay, now then we go back to the original wideband power control scenario. And to investigate this foresighted issue, first we need to define the so-called stable equilibrium. So for stable equilibrium, we need to have one foresighted user, and also multiple myopic followers. So for this foresighted user, he needs to determine an action based on the following rules. So once he picks up an action, he's aware of the response of all the other myopic followers. And for this foresighted user, he will choose the action of this AK star here. This AK star will lead to himself a utility that is not worse than all the other feasible action in its own action set, meaning that this foresighted user is aware of the reaction of the other myopic users. Then he will simply choose the best action that brings the best performance for himself. Okay, then we prove that the existence of the stable equilibrium is always, we always have a stable equilibrium in the power control game. This is simply because this mapping is continuous and it is upper bounded. So this upper bound is called the single user water filling bound, meaning that assuming that the other users creates no interference to this foresighted user, this is the best rate that this foresighted user can get in the interference-free environment. So as long as the other user creates interference to him, and his attribute rate will be less than this upper bound. Okay, then the next question is, how can we find the stable equilibrium, and how much better this stable equilibrium is compared with the natural equilibrium? Because intuitively, it should not be worse than the natural equilibrium. So we start from a very simple two-user scenario. It can be extended to the multi-user version, and we can formulate it as a bi-level programming problem. So here we assume this user 1 to be the foresighted user. For this user 1, he needs to determine his power allocation, which is a vector. That this power allocation will maximize its own attribute rate. Please note that here, when user 1 forms this particular program, he needs to consider the reaction of this user 2, because user 2 will simply choose the water filling solution. And so basically, this bi-level program consists of two sub-problems. The first is upper-level problem, and actually in the original iterative water filling solution, this foresighted user only solved the upper-level program. He will totally ignore the lower-level program. So if the user becomes foresighted, he will form such a program. And the question is that, having such a bi-level program, how can we compute the stable equilibrium? Okay, so we trying to understand the computational complexity of this such stable equilibrium, and trying to, based on the understanding, we propose some low complexity algorithm to calculate the stable equilibrium. So in order to handle the original bi-level program, we need to reformulate it into a single level problem. So we introduce a function named the water filling function here. So basically, this water filling function will determine the user 2's allocated power at different frequency beams, given the power allocation of the foresighted user and user 2's own noise, spectrum density, cross-channel gain, and also its own power budget. So here's the closed form expression for this water filling function. It looks complicated. However, the intuition here is very simple. We can look at the illustration here. So let's say this is the user 1 choose some feasible power allocation, and this is the spectrum that user 2 this is the user 2's receiver's spectrum. And we can see before user 2 determine his power allocation, he needs to do the following things. First, he needs to rank his channel based on the channel condition, from the best channel to the worst channel. And the second thing he needs to do is that, based his own power budget, he needs to determine how much channel I need to occupy. And he just simply increase his water level until he uses up all his power budget. And then we can see from the closed form expression for the water filling function is that first we need to have a permutation which rank user 2's channel condition based on its own channel condition. And the second thing is that we need to determine some number of the channel such that user 2 will only access this channel. So as we can see from this closed form expression, because as long as user 1's water level go across the boundary between different frequency beams, which will cause this function to be the left derivative and the right derivative to be unequal. So which creates this water filling function to be non-differentiable. And while at the same time, we can see here, this power term, this P1F, also appears in the denominator term in the objective function, which creates the objective function to be non-convex. So this caused this optimization problem to be very hard to solve. But however, we noticed that there exists some literature applying the dual algorithm in the non-convex power allocation in the literature. And we're trying to apply this method in our Stepberg equilibrium computation and to see whether or not it's suitable for our scenario. So to apply the dual algorithm, so basically we have the primal problem here. Then by having the primal problem, we form the Lagrangian dual, and by maximizing, for given a Lagrangian variable, we maximize the Lagrangian dual, then we have the dual function. Then by minimizing the dual function, we have the dual optimal. So firstly, we show that for this Stepberg equilibrium, the dual gap may not be 0. However, this dual optimal, if the dual gap is not 0, this dual optimal will be strictly tighter than the original single user water filling bound. And at the same time, we show the monotonic property of this dual function in terms of the Lagrangian variable, meaning that if I increase the penalty term of the Lagrangian variable, and definitely the dual function will decrease as I increase the penalty. And the most key things is that how is the complexity of solving this problem in the dual domain? Unfortunately, it still has the same complexity as in the dual domain, which causes this problem cannot be decomposed into different per subcarrier problems. So why this cannot be reduced? Because in the water filling function, in these slides, user 2's allocated power not only depends on user 1's allocated power in this particular frequency beam, it also involves some allocated power in the other frequency beams. So which causes this problem very hard to handle. So the key idea here to propose a low complex solution is that instead of solving the Lagrangian globally, we propose to use the local maximum to approximate the dual function. Then we just need to find the local maximum of this Lagrangian variable and use this to update the dual function. The advantage is that we have very low complexity solution, and it's not purely based on heuristics. And we also allowed arbitrary number of myopic users. Okay, then by applying this low complexity solution, we simulate a wide range of channel realizations. And here's something interesting happens. So we found that by introducing such a foresighted user, using this low complexity solution, this foresighted user always achieves better performance compared with the iterative water filling algorithm. Meaning that if the user gets the global information, he chooses another action, he will definitely benefit himself. While on the other hand, for these myopic followers, surprisingly, these myopic followers also, in the most of realizations, these myopic followers also get strictly better performance. So it means that if this foresighted user, even though he's trying to maximize its own utility, the other myopic followers also get better performance. So this is quite unique because in the original game theoretic scenario, people don't have a generalized solution, a result about in the stepper game how's the performance of the follower. So it turns out in the water filling game, the follower's performance also gets better. Okay, how this is achieved? So let's look at the action domain. So these two figures shows the power allocation for both users, and the upper figures shows the power allocation using the iterative water filling algorithm. We can see here, if both users apply this water filling algorithm, then they will just use this best response. However, if this user 1, he gets foresighted, then he will choose to not water fill his power. He will just occupy some channel that is, in that channels, he has very good channel conditions by putting a lot of power in these channels. And while at the same time, he will keep the followers away from this channel. And by doing so, he can achieve much better performance compared with the water filling solution, even though he can gain immediate increase by water fill in these channels. However, it turns out if he water fill in these channels, in return, the other user will occupy this channel, which results in a worse performance for himself.
So in this basically particular case, just look at the example. Are you assuming, for example, user 1 and user 2 has some kind of different channel transfer properties?
Right, exactly.
So I mean, that's why, for example, channel 3 and there's 7 to 10 is more favorable channels to user 1, right? Okay.
Yeah, that's the basic idea of frequency selective. Yeah.
Okay. And how achievable is that in the real world case?
Okay, so basically in the DSL system,
yes.
So this channel coefficient is fixed. It's fixed over time.
But you need to discover it.
Right. So
channel condition which is fixed over time, I mean, may not be. I mean, channel condition actually change in wireless level.
yeah.
Right?
So yeah, the original power control this water filling game is proposed for the wired system,
Okay.
for the ADSL and VDSL system. So for their case,
Which,
yeah, it's not a problem.
yeah.
So so here in the first part of this talk, we assume that they know this information.
Okay.
And in the next part, we will relax this assumption, and they will learn this information.
Okay.
Okay. So the conclusion so far is that we have the non-cooperative setting, and however, if some of the users they get foresighted, he's able to know the structure of the game he's playing, and potentially he can improve the performance for all these players. Okay, as I just mentioned, in order to play this stepper equilibrium, we assume that this foresighted user have global information, which might not be very realistic in the in real systems. So a more realistic assumption should be for this foresighted user, he should only know the interference that the other user caused to him, the aggregate effect the other user caused to him, not the detail of the cross-channel transfer function of the actual game he played. So our next investigative problem is that if this foresighted user only knows this aggregate effect, how should he explore this structure and also attain some desirable performance that is similar as the stepper equilibrium? So the intuition that here, this foresighted user, he should somehow model the accumulative interference of the other user caused to him. Okay, then now we relax this assumption and to see how this user should react. Okay, in order to model the mutual coupling, we need to reformulate the game that we originally designed. And first, we need to introduce a new concept, which is called state. So the state means something that value that has direct relation for different users to different users' utility function. So given a state, given the user case state, and given user case action, it will directly determine this user case utility. So in particular, for example, in the power control game, this state will be the interference the other user caused to him. So by defining this state, we need to have this state determination function. So this state determination function will capture the actual play of this particular game. So it will capture the aggregate effect of the other user action. So it will be a joint mapping from the joint action space to individual user state. And on the other hand, we need to have some internal belief. So we need to have a belief function. So this belief function will be a mapping from individual its own action space to its own state. So meaning that this belief function will represent individual users' internal modeling of how its action will impact its own state. So it's a purely internal belief from individual users' own perspective. Now we are ready to define the conjecture equilibrium. So what does conjecture equilibrium means? So basically, it's a configuration of belief functions and a joint action set. And at the conjecture equilibrium, each user, first, he finds that his beliefs are realized. He knows that if he takes certain actions, it will bring him certain state. And this state it will be confirmed by the actual play. And on the other hand, he will maximize his own utility function by believing that by playing this certain action, and it will bring him such a state, and this action will maximize his utility function. So now we decoupled the multi-user interaction, and user just hold its own internal belief, and it will perform as a best response with respect to its own internal belief. Now we are ready to apply this conjecture equilibrium into the water filling scenario. Okay, so in the power control games, the state space is simply defined as the interference the other user caused to him. And the utility function is still the same as the previous case. And the state determination function, this is the actual play. Each user's allocated power will directly determine his received interference. So the belief function in this case, we'll choose it as a very simple linear form, and we'll explain why this makes sense. And here, individual user will just simply believe that if he increases his allocated power in frequency n, and the interference that he's gonna experience will be decreased by a certain amount. It's basically his internal belief. And okay, here's the main result we prove. So firstly, we show that the aggregate interference the other user caused to this particular user will be a piecewise linear function of the allocated power of this particular user in this channel. And the first order derivative with respect to the allocated power in the other frequency bins will be 0 if the number of frequencies is sufficiently large enough. So which means that the first order information is sufficient enough to capture the multi-user coupling in such a multi-user power control games. So the intuition is, we'll explain the intuition here. So let's say this is user 2's spectrum. He originally performed the water filling. Let's say user 1 increased his allocated power in this frequency bin by a certain amount. And if he increased the certain amount, and user 2's water level will definitely increase. However, if the number of frequency bins is sufficiently large, then the increase of the water level will be negligible. So which means that the allocated power in other frequency bins, the increasing of the power level in the other frequency bins will be 0, and while at the same time, the user 2's allocated power in this particular frequency beams will be reduced as a linear function of the user 1's increased power. In return, user 1's experience interference in this particular channel will just simply a linear function of its own allocated power in these frequency beams. So this is the basic intuition. And second thing, we show that in both the previous case, the Nash equilibrium solution and the stable equilibrium solution are just a special case of the conjecture equilibrium, corresponding to different parameter setup in the belief function. So in the Nash equilibrium case, the foresighted user will just simply set up the first order term to be 0. While at the stable case, this foresighted user, he need to select his he need to set up his parameter gamma to be the negative of the first order information of its own allocated power. And the third result we have that is actually the open set of conjecture equilibrium exists in the belief domain. So now, since we are mostly interested in achieving the stable equilibrium of only have local information, then the next step is simply how should we properly set up the belief function of beta and gamma in order to attempt to approach the stable equilibrium by only having local information. Then we propose a dynamic update. So for this foresighted user, during each iteration, first he needs to estimate the first order information, the first order derivative of the aggregate interference the other user caused to him as a function of its own allocated power in different frequency beams. By estimating this information, he will include this first order information into its own optimization program. Then he will update his allocated power. Then he will re-estimate the first order information. And they will do this iteratively until no further rate improvement can be achieved. Then we have this conjecture-based rate maximization algorithm. And the essence of this algorithm is actually a local approximation of the bilevel program. Because we explore the structure of the water filling game, because simple linear belief makes sense in this scenario, so we can improve the performance of this multi-user power control scenario by only have very simple linear beliefs and only having local information. The simulation result shows that it achieved comparable performance of the previous case where the foresighted user possess global information. Okay, so the conclusion so far is that if foresighted user possess only local information, if he's able to make correct belief, and potentially he's still able to improve the performance of himself, but also the other players. Okay, then the next question is that, what if we have multiple foresighted users, and all of them is trying to learn and adapt? It turns out it might be difficult at this stage because for this power control game, the action set is actually a vector set. It might not be that easy to handle. However, we are able to discuss this problem in another different setting, so which is the wireless random access. So we allow multiple foresighted users and often just have local information. And we also apply this conjecture-based approach and to see how it will shape the multi-user interaction in such an application scenario. So basically, we investigate multiple nodes in a single cell. So the action set for each user is just to determine transmission probability, and the payoff is given by the throughput, just as Professor mentioned before. So it's given by its own transmission probability times the probability that the other user doesn't transmit. So the key issue of this multi-user interaction scenario that people are mostly interested in is the stability of your algorithm, the convergence of your algorithm, and how is the throughput efficiency and fairness in such interaction. As we have seen before, if user is purely myopic, he will set up this probability to be 1. Then the network will collapse and nobody can get through. Okay, then we investigate the conjecture-based approach in such a scenario, and very simple. We can define a state to be the probability that for each user having a contention-free channel. This is the probability that for this particular user K, he has a free channel. Then this state is actually a local information. It just monitors the aggregate effect of the other user close to him. Then still, individual user just develop linear belief. And for each iteration, each user will believe that by deviating my current action by a certain amount, and it will in return reduce my probability of having a free channel by this amount. Then we are mostly interested in the limiting behavior of such dynamic process. And we investigate two different update mechanisms. First is the best response scenario. Each user just update their action based on the best response. And the second scenario is they just update their actions along the gradient direction. Okay, so here's the actual play. Here's the conceived play. And we have four major results. The first result we have is that all the action sets in the all the operating points in the action space actually conjecture equilibrium. This has nothing to do with the stability. And the next result we have is that we investigate the stability in the throughput. We provide sufficient condition about the stability and convergence about these two dynamic update algorithms. And by having this sufficient condition, we are able to show that actually the entire throughput region is spanning from the original Nash equilibrium to all the way to the Pareto boundary are just stable conjecture equilibrium with respect to different belief setup. And the fourth result we have is that actually at different operating points, these multiple users actually obey the weighted fairness rule. So by having these four results, it means that if we design this conjecture-based approach properly, we'll simultaneously have stability, convergence, efficiency, and also fairness. Okay, these slides explain why users can achieve weighted fairness. So the definition of weighted fairness is as follows. So this formula gives the probability of this user I of having its packet get through. So weighted fairness just means that each user's probability of having a successful transmission is weighted equal. It's proportionally equal. And by simple manipulation, we'll have this formula among different users. And we, at the equilibrium of this conjecture protocol, we find similar results given by this formula. And we know that if the number of users in the entire network is large enough, and the probability of transmission for each user will be close to 0, then definitely we can have these two equality approximately the same. So the next question is that how should we set up the belief function in order to obtain the Pareto efficiency? And the key idea is that they need to adapt. They need to, because these users, they have access to the same common observation, because the outcome, they know exactly which packet gets through. So they will simply adapt this parameter in their belief function until they found that they cannot further improve the system performance. Okay, the advantage of this solution is that we don't need to have a centralized solver. And they just operate based on their local information. And the resulting operating points is throughput efficient and also fair. And it can autonomously adapt to the traffic fluctuation. So in these slides, we'll present an engineering interpretation of this conjecture-based approach to explain how it is different from the DCF protocol. And this is the original update formula for the best response scenario. And we can actually decompose it into several different terms. These different terms correspond to, given the transmission probability of all these users, based on the observation of the previous transmission, how the probability of these different users will evolve in the next time slot. So basically, it's described the deterministic trajectory of the multi-user interaction. And then we just fill in this table. This represents the conjecture-based random access. And we can see here, if user 1, he observed the other user make a successful transmission. For our best response scenario, he will choose to reduce his transmission probability by a factor 2. And similarly, we can fill in these blanks for the other observations. Then we have our protocol of this conjecture-based approach here. Then also, we can have the currently existing DCF protocol here. So basically, what DCF performs is that if I did not transmit in the previous time slot, I will not change my transmission probability. I just simply reduce my contention window by a number of 1. And if I observe a collision, then I will reduce my transmission probability. If I make a successful transmission, I will increase my transmission probability. As we can see here, our proposed approach is actually similar in the case that I made a transmission attempt. This is similar as the DCF protocol. However, what is different is the case that if I did not make a transmission, but still I need to make some modification of the transmission probability of the next time slot. Why this is interesting is because even though I did not transmit in the previous time slot, I still observe something from the joint play. And I know that if the channel is congested or not, then I should also be able to adapt my next transmission action in order to timely adapt to the network fluctuation. So this is the basic idea. So which means that the conjecture-based random access actually is making use of 4-bit information compared with the DCF case, which only 2 bits information is explored. Okay, so here's the simulation result. And we can see here that the DCF is not efficient as the number of nodes increase in the network. And how the PMAC protocol is actually proposed by people from University of Michigan at IWCOS. And in this case, they need to know exactly the number of nodes in this work, and they are able to develop some approximately develop some closed-form expression of the transmission probability that enable to achieve very high level throughput. And it turns out by having this conjecture-based algorithm, we can also beat this PMAC protocol by having no information about this protocol, about the actual network, but just adapt based on the actual outcome. And however, for this PMAC protocol, since they need to know the number of nodes, and in the actual implementation, people need to online estimate the number of nodes. So which caused this protocol to be unstable because it's an open loop. There's no closed loop control. And because of our game theoretic design, we show that this equilibrium is stable. So we can see as even though the number of nodes, we change the number of nodes in the system over time. We can see here, actually, the conjecture-based algorithm actually can still sustain the stability of the operating point over time. So the conclusion so far is that if everybody only have local information, and if we design the belief function correctly and properly, still we can able to improve the system performance. Then the key idea is just to, based on the problem of your investigate scenario, how you should design your belief function and update it. So the future direction is that we are trying to understand for which type of multi-user interactions this conjecture-based approach is suitable. And also, based on the information availability in different application scenarios, how we should choose appropriate equilibrium concept and how we can compute it, and also its stability, convergence, and fairness. And we're also looking forward to apply this conjecture-based approach in different applications. And based on the presented work, we have 2 accepted journal papers and also 1 more pending. And we also published 2 more conference papers. These are all archival transaction papers. Okay, thank you.
Thank you.